I have done 2 projectile motion examples so far. The first one answered the question, how far? The second one was a horizontal projectile, and this one is going to answer, how high does something go? So as always, we start by drawing it out. So if our object is on the ground, and it is going to be shot up at an angle of 68 degrees, and it's going to be going 85 meters per second. So what was it? It was 68 degrees and 85 meters per second. And we have to figure out, how high does it go? So if we're going to draw a projectile motion, it's going to look something like that. Now, here's where the thinking bit comes in. It only wants to know, excuse me here, let me fix that for us. It only wants to know how high. That means it needs to know this. So all of this stuff right here, we don't care about what happens after. We only care about everything that gets us up to that point that is how high. Now the other thing that we see in here is we see that it is a vector. And every time we have a vector, we should automatically just say stop and break it into components. Just do it automatically. Alright, so here I'm going to do that. If this is what I've got, let's go ahead and draw it out. It's going to have, whoops, here is our x component, and here is our y component. Now, horizontally, what you're talking about is the cosine. So our initial velocity in the x, all right, and remember actually it's just our x velocity because x velocity is constant in projectile motion. Our x velocity is going to be hypotenuse times the cosine of theta, and that is 85 cosine of 68. And that value is 31.8 meters per second. Do the same thing in the y. And in the y, the initial velocity in the y direction is going to be the sine, because it's the opposite leg. So it's h sine of theta, which is 85 sine of 68. And that value is 78.8 meters per second. I'm going to kind of do this long way, and then I'm going to talk to you about something else, so bear with me. So let's go ahead, we're going to put everything into the table the same way we do every time. Okay? So we know we have our acceleration in the x, we have an acceleration in the y. Horizontal motion is always constant, so there's no initial or final, it just is. We have our initial in the y, we have our final in the y. We have a displacement horizontal, we have a displacement vertical, we've got a time. Okay, now, I'm going to apologize if I repeat myself, but I was interrupted briefly. Now, I just wrote down the list of all the variables, and before we go any farther, I want you guys to take a look at it and think about what's happening. So these are all of our variables. We have all of our x, and we have all of our y. We haven't filled them in yet. That's okay. But look at what we're looking for. What part are we looking for? We only care this time about our delta y. And so if we can, we're going to try and solve this just in the delta y. We may not need anything from the delta x because what we're looking for is all vertical. I'll put down all of our variables, but we'll take a look at the end to see, do we actually need any of it? Okay. Switching colors here. All right. And our x is always going to be constant motion, constant velocity, so there's no acceleration. The initial velocity in the x, or rather the velocity in the x, was 31.8 meters per second. Our delta x, we don't know it. Our time, we don't know it. Now, over on the y-hand side, let's take a look at that. Acceleration is always negative gravity, which is negative 9.81 meters per second squared. Our initial velocity in the y is 78.8 meters per second. And our final velocity in the y is 0 meters per second. What? Where'd that come from? That came from the fact that we're only looking for the height. All right, and our height, that maximum height is the maximum, is at the place where the ball or object turns around. And in that moment of turning around, its velocity is 0. The maximum height will always give you a velocity of 0. So we have that, and we're looking for delta y, and we don't know t. Now take a look at what we have here. You've got 3 knowns and 1 unknown. That's all you need to solve a problem. So in this case, when you're looking for how high, you don't need any of the x stuff. You don't need any of it. We're just going to use just the delta y stuff. Now, for this one, if we're looking for delta y, we're looking for the height. That means we don't care about the time. And the equation that we're going to use here is final velocity squared equals initial velocity squared plus 2 acceleration times my vertical displacement. And we're going to solve for delta y. Let's start by moving our initial velocity over. It's going to cancel out, and we are left with vf squared minus initial squared. Both of these are in the y direction. Is equal to 2a times our vertical displacement. We're still solving. I'm going to get rid of the 2a. Divide both sides. Okay. So we can go ahead and cancel this. And our final velocity, if you recall, was 0, so I'm going to get rid of that. So we're now left with minus my initial velocity in the y squared divided by double my acceleration. Now please note I said minus. It's not a negative, it's minus my velocity. So put in some numbers, so it's minus 78.8. And we're going to square that 78.8. We'll divide it by double our acceleration. Okay. Go ahead. Now the negatives are going to cancel out, and when you solve it, you get using our sig figs 317 meters. That is how high it's going to go. And that is our third example problem. Enjoy.